During this week, many of the lecturers and speakers, basically almost everyone, mentioned at a certain point the Calogero Moser system, so it's really honor to have here one of the main contributors to the startup of this subject, which is coming out and being generalized in many ways. So it's one of the most relevant integrable systems. So thank you very much, and please today Francesco will talk on dynamical systems solvable by algebraic operation. Please.
Well, thank you very much, Simonetta, for inviting me, for organizing this very nice meeting, and for the nice words. Yes, I will not talk about the Calogero-Moser system. In fact, I will talk about very recent results. I suppose you all read this because it has been there for some time. I will talk essentially about results in these two papers. One has been published quite recently, and the other one is not yet finished. It's essentially finished, but not yet submitted. And I will mention them and explain what is their relevance. These results are a follow-up via one or two additional tricks, so to say, to the material that is mainly in this, which is the reference to, so as often I refer to this. This is also a relatively recent book of mine, and something on the first book of mine also. So, yes. So what is written there is that I mainly report the findings of these two papers, and the idea on which all these results are based is a very simple one. So I will always fly very low. I'm not able to go to algebraic geometries, real things. I mean, I am very much doing simple things. The idea is a very simple following basic idea, which is also behind the results, for instance, in the book. Suppose you have a polynomial of degree n in a variable in the argument z, and that polynomial depends on time. We'll always work with complex variables. So such a polynomial, if it is a generic polynomial, will have n coefficient and n zeros. So I maybe should really look and show the formulas. This is a polynomial. I'll always assume that it is monic. So a polynomial of degree m as m coefficients, as you see here, and I call them ym. And then a polynomial, a generic polynomial, has n zeros, and the idea of many of the results of the general approach is that you assume that the coefficients evolve in time in a way that you can control. In some sense is solvable. We can see various examples. And then look at the evolution of the zeros. Then, of course, since to go from the coefficient to the zeros, it is an algebraic operation, then the evolution of the zeros will also be algebraically solvable, and that is the idea, to get many new algebraically solvable systems, and maybe later we'll see why it is interesting to have this class of algebraically solvable system, and in a sense, well, okay, in some sense it's a new class with respect to a very classical class that has been studied a long time ago. But the new twist on which I will base this talk is to look not at the generic polynomial, but to a non-generic polynomial which has m coefficients, so a polynomial of degree m in the variable z, but as less zeros. So some of the zeros, of course, have to be multiple. So this is the basic formulas, m is of course larger than n. N is the number of zeros. The zeros are indicated as xn of t, and mu n is their multiplicity. So the mu n are positive integer numbers. And of course, you immediately can check that the sum of all the mu m must just be m, just comparing these formulas. And it is also obvious that you can express the coefficients in terms of the zeros by explicit formulas, which are sometimes they're called, for the general case, the generic case, the Vieta's formulas. This is an example. This is for the first, y1 is given explicitly in this way in terms of the zeros, and the last one, ym, is given by this formula, but all of them. And then we'll eventually go to simple examples to see, but that's the general setup. A few remarks, rather obvious. You see, if you have a generic polynomial, you can define it by giving arbitrarily, always monic polynomials, you can define it by giving arbitrarily its n zeros or arbitrarily its n coefficients. If you have a non-generic polynomial of the type that I'm considering, you can define it by giving arbitrarily its n zeros, but you cannot give arbitrarily its m coefficients. You can only give n of the coefficients, but the others then will be determinate. So these polynomials have this peculiarity that you are not free to assign all the coefficients, and that will be very important in what follows. Another thing is that, of course, is very trivial, that if for a generic polynomial, for a polynomial in general, there is a difference between the zeros and the coefficient in the following sense. If you have a generic polynomial, the coefficient are an ordered set. So it's a vector made of the coefficient. The zeros are a non-ordered set, because the polynomial, you have all the zeros, but you don't know which is the zero number 1 and the zero number 2. That is, you can assign freely. This, however, is not true if your polynomial depends on time as an extra variable, because then these zeros are, once they're assigned a label 0, 1, 0, 2, 0, 3 at time 0, if the evolution is continuous, then their labels remain fixed. So they are distinguishable for all time. Okay, these are already elementary remarks. And in the case on which we focus of a polynomial which has zeros which have a multiplicity that may be different from 1, of course the zeros at different multiplicities are for all time different objects. And so the question is how to use this tool. Yes. You see, this polynomial, you must think of it as a tool to obtain results. Grazie. And the results, as I say, the whole idea is that then you will take evolutions for the coefficients that you know how to manage. They're solvable. We can see what it means, maybe explicitly solvable. Yes?
Multiplicities are fixed, so you assume your polynomials.
What?
In case of non-generic polynomials, you assume that your polynomial is such that the multiplicities are independent of time.
Yes, the multiplicity are fixed, so the polynomial will have the same multiplicity for all times. It's a tool to obtain results. Yes, the multiplicities are time independent. And so we have to learn to use this tool, and the next part is how to use this tool. So using this tool means that we want to have, if we know how the coefficients evolve, and I will always deal with the very simple case of first order evolutions in time. So the coefficients will evolve as first order ordinary differential equations in time. What is the corresponding evolution of the zeros? And the important development is that you can write them explicitly. This was already an interesting development for ordinary polynomials and for generic polynomials, and allowed to obtain many new solvable systems, and that is treated in my book, my last book. But now we want to extend this to this more special case. So to do this, the first step is that you differentiate. Remember, there are these two expressions of the polynomial in terms of its coefficients or in terms of its zeros. This is the same polynomial. And now we differentiate the expression firstly once with respect to time. So this is the usual notation for differentiation. The differentiation of the expression with the coefficients is very trivial. You just differentiate the coefficients. And the differentiation of the expression with the zeros is rather obvious. It's given by this formula. The next step that we make is to differentiate this expression with respect to z many times. I will in a moment tell you how many times. And then we set z equal to one of the zeros, xn. So if we differentiate this mu times with mu 0, 1, 2 up to mu n minus 1, and then set z equal to xn, then from this formula, I should have gone back. Yes. From this formula, you see that this expression will give 0. If you differentiate this with respect to z less than mu n, in fact here I have to look, mu n minus 1 times, then this right side gives you 0, and then the corresponding expression is simple because you have differentiated with respect to z many times. So you will get a lot of expressions in which you have 0 on the right-hand side, and what you will have are linear expression in the ym dot, because you only differentiate with respect to z. And then there is also the case in which you differentiate mu n minus 1 times, and then you will have something that is different from 0. So in this way, these are the two classes of formulas that you obtain. These are all with the zeros, and these are true for mu equals 0, 1, mu n minus 2, for all values of n equal 1, 2 to n. So you have a lot of these formulas, so to say, and they're all linear in the derivatives of ym. And then you have for these other formulas in which you have set mu equal to mu n minus 1, in which on the right hand side you have xn dot, which remains, and again these are explicit formulas. And so these formulas allow you to compute xn dot, the derivative of the 0, in terms of the derivative of all the coefficients, however, all the ym. And that is the formulas, the relevant formulas. This is the derivative of a 0 of a polynomial of this type in terms of the derivatives of the coefficients. You see, but now in this approach in which you have more coefficients than zeros, as I told you, you cannot have equation of evolution for all the ym, because the ym are not independent from each other due to the fact that they are the coefficients of a polynomial of this spatial kind. And so the point is that now we have these expressions that give you the evolution of the zeros in terms of the coefficient, and then you have a lot of relationships between the zeros, and you convince yourself that you have, in fact, n equations for the evolution of the n zeros, and then you have big M minus big N equations which are linear equations in the coefficients, in which the zeros, of course, enter. Now we'll see very simple examples of this, and everything will be more clear. So, in this way, with the notation that I've taken, is that you divide the coefficients between a set of n coefficients. N is the smaller number, there's a number of zeros, and the remaining ones. And you want to express everything in terms of this subset of coefficients that you can choose arbitrarily. You call them ym tilde. This is just a notation. And then you have a linear relation between the derivative of these. And so this is the approach. And what I've described to you shows that it works. You can do it. But then to have examples, you have to look at specific cases, because each case is different. And so in this talk, and in fact in our paper with my Iranian colleague is Farin Payande, we have looked at the case with m equal 4, so polynomial of degree 4 with 2 zeros. And then there are two possibilities. Even the 1 0 has multiplicity 3 and 1 has multiplicity 1, or both have multiplicity 2. And in this, we treated both, but here I'll talk only on the case with 1 and 3. And so this is the polynomial. Now everything is very simple and explicit. You can see this is a polynomial of degree 4, which has 3 zeros, which you call, a 0 x1 with multiplicity 3, and a 0 x2 with multiplicity 1. And these are the coefficients, 1, 2, 3, 4. There are 4 coefficients, of course. And these are the explicit relationship of the coefficients in terms of the zeros. And so these are all the explicit formulas. And now what I have in the next slide is for this special case, you see these are the relationship between the derivative of the zeros. These are linear relations. And in this case, you have two of them, because m is 4, n is 2, so you have m 4 minus 2 is equal to 2, so you have two relations of this type, and then you have two relations instead which give you x1 dot in terms of the zeros and x2 dot in terms of the zeros, and you see all coefficients enter here, not in this one, but in this one, they all enter. And now you can make a choice of which coefficients, the evolution of two coefficients you choose as the one that you suppose then to be solvable. And in this way, in this particular case, you get, of course, 6 equations, because this 6 equation has, you see, they give you explicitly the evolution, the derivative of x1 and x2 in terms of, in this case, y1, y2, y1, y2, in this case, y1, y3, y1, y3, and so on. So you have 6 possibilities. These are all identities. They are identities in this framework. And then the idea is that you can choose an evolution for two quantities, call them, you can choose y1, y2, y1, y3, y2, y3, and then from these evolutions, you get the corresponding evolution for the x's, which in general will be much more non-linear. Even if the evolution for the y were linear, the evolution for the x's would be non-linear, and if the evolution for the y was solvable, the evolution for the x's will also be solvable. Okay, now just...
Sorry, one of your situation, the derivatives of y's are dependent only on y1 and y2, not on y3 and y4 as well.
Yeah, no, this is because, you see, in all cases, the derivative in my previous formula dependent on all the coefficients. But then the coefficients are related to each other by linear relations. So I solve the linear relations.
By linear relations.
Yeah, and so by solving the linear relations, I can express the derivative of x1 and x2, the two coefficients, in terms of any one of any two, so to say, of the two. This is the basis of the trick. Of course, then if I will have a solvable evolution, say for y2 and y3, and put it in, it will be very different from put it in because then the expression of y2 and y3 in terms of the zeros is different. And you notice that in all these relations we always have the denominator x1 minus x2, and then sometimes we have other denominators when you have higher derivatives. Okay. So that's the first, so to say, trick and idea, to focus on these non-generic polynomials as a tool. The second idea is that one would be very interested to have evolution equations in which the right-hand side is a polynomial. This is, first of all, for purely mathematical reasons, because they are the simpler case in a sense, and secondly, for many, many applications. In many, many applications, you have equations for the evolution, the simpler case of two quantities, with the right-hand side being a polynomial in these two quantities. And then, how can you achieve this? Well, this is a very simple trick. You just must have an evolution for y1 and y2 that has the property to be proportional to x1 and minus x2. To be, first of all, you have to have polynomial evolution for y1 and y2, and moreover, such that when you put y1 and y2 in here, you get a polynomial, however, a polynomial that has the factor x1 minus x2. So a polynomial that vanishes when x1 is equal to x2. And that's very, very simple, and it is a general fact in all this approach, but I illustrate it in this very simple case. So in this simple case, I just take the simple case of x1 and x2 depending on y1 and y2. But the same thing then would be true for any one of the others. And so the equations that we had before were these equations. You see f1 and sorry, I should have emphasized that I am now assuming this evolution for a y1 and this for y2 given by this function of y1 and y2 and y2. I will give an example in a moment of such a solvable equation, and then by putting them in, what I get are these expressions here. So you have f1 here of these two arguments, which are y1 and y2 expressed in terms of the x's, and the same for f2 and so on. And you see immediately that you want now to look at the case in which you assume f1 and f2 to be polynomials, and you assume this polynomial in the numerator here and here, both of them, to have x1 minus x2 as a factor, namely to vanish when x1 is equal to x2. And you see immediately that the condition for both cases is just this one. It should be that 3x f1 of f1 computed at minus 4x 6s squared, and plus this, which is what is in the numerator. In both cases, it reduces to this, should be 0. So in this way, if we restrict our attention of the evolution of the two y's, which we can choose among the various possibilities, to evolutions which are solvable with polynomial right-hand side, which satisfy this condition, we will get the evolution equation for the x's, which have the property to have polynomials in their right-hand side. Let me put my watch here. I have to watch my time. So let's immediately look at an example. Let's take that the evolution for y1 and y2, y1 dot equal to something, they are of this type. And then if this condition is true, you immediately can see that then the right-hand side will vanish, of those equations will vanish when x1 is equal to x2, so they are suitable. In addition, this system of equations, y1 dot equal this, y1 dot with this assignment, is, if you differentiate this again with respect to time, it gives you this equation using this one, and this is the equation for the Jacobian elliptic function, so this is a system solvable in terms of Jacobian elliptic functions. The corresponding evolution for the x's, which maybe I will write immediately. Yes, this happens to be the evolution in the x's, where this a and b are two arbitrary parameters related to the previous one in this way. So now you can say that this is a solvable system, solvable in the sense that you can solve it by algebraic operation. You give x1 and x2 at time 0, you compute y1 and y2 at time 0, you let the y1 and y2 evolve, and they are elliptic functions, and then from these elliptic functions you can reobtain x1 and x2 at time t, and your last operation is algebraic. In fact, you have only to solve an equation of second degree. As a consequence, the solution of these two equations in general will not be, even if the evolution of y1 and y2 is meromorphic, one valued, the evolution for x1 and x2 is only algebraic. It will not necessarily be meromorphic because you always have eventually to solve a polynomial equations to get them. And so this is, in a sense, introducing this new class of solutions of this type of problems, which we think is an important new class. It's the class of problems which have solutions which are algebraically solvable. But I have to hurry up. And, well, okay, this is an example, and so this is the technique that you can follow. This technique is introduced in this way via polynomials, but essentially it's a technique to perform a nonlinear transformation between the variables x1 and x2 and two new variables, and then have this transformation be algebraic, and then have the evolution of two of these variables to be controllable, and then the evolution for the other two to be controllable. So it's a very simple general idea. The question is that you can write explicit equations and have a lot of examples. And in the paper 3, which is the paper with my colleague Farin Paende, we have applied this technique in this simple case of 4 and 2, and we obtain, in fact, 34 different systems, and I show you some examples of this. Of course, not all 34 are given in the paper. You see, you always have a system of two equations for x1 and x2 of this type. They are all polynomial, those that we have chosen because of this technique. And, well, you have an idea. All these systems are algebraically solvable. And here there are 1, 2, 3, 4 such systems, and then you have 1, 2, 3 more. As I said, there are 34 of them. Some of them have some denominators. The x1 minus 2 is always eliminated, but you may have 1 over x1 or 1 over x2 in the right-hand side. Okay. All right, now I would like to turn to the results which are in the second paper, the one with François Levras and Robert Comte, which, as I said, it's not yet finished. I mean, the authors are far from each other. One is in Mexico, one is in France, but was in China until lately, so the progress is slow. However, before going to these results, let me remind, some of you know it, of course, very well, that there is also another trick in this field, and the trick is the following. If you look at this system of evolution equations, you see this is now a system in which in the right-hand side you have the dependent variables that evolve are the xn dot. I restrict attention again to n1 and 2, but these results will be true even more generally. And in the right-hand side here, I have a polynomial which is homogeneous of degree L plus 1, I guess. Okay? No, of degree L, I'm sorry. This is a polynomial of degree L in the two variables x1 and x2. And then there is this extra term here. And the simple trick is that this system can be, which is, of course, it's an autonomous system. And omega, I assume, is a real variable. L is an integer. The C and L are arbitrary coefficients, time independent. And these are the dependent variables with a tilde put on top of them for convenience. And then if you make a change of variables, both of dependent and independent variables, I call it the trick, this type of change of variables, then you see you have put this prefactor here, and now you have this xn of tau, and tau is related to time t in this way. So when t is 0, tau is also 0, but when t evolves as real time, as a real variable, tau moves in the complex plane on a circle. Therefore, therefore, if this quantity, if this function xn of tau is analytic in tau, then the function xn of t will be periodic, more than periodic. It will be isochronous, because it will be periodic with a period which is just 2 pi over omega, if the function xn of tau is analytic. If xn and tau is not analytic, but it is algebraic, in other words, it only has branch points which are of algebraic type, then still xn of t will be isochronous. So all solutions will be periodic with a period which is an integer multiple of 2 pi over omega. So this underlies the interest of models of this type, because then by this simple extension from the xn to this is now xn of the prime indicates derivative with respect to tau. It is just to emphasize that models of this type, which are algebraically solvable, are particularly interesting because just by this extension to this, the same model, but just with the addition of this term in front, you get a dynamical system. Now, of course, inevitably complex, because there is this I omega in front, which, however, has the property to be isochronous. I mean, to be isochronous, namely, all solutions of this system have the same period. Some may have a smaller period, but still, they all have the same period. This is, of course, a very, very strong restriction, and in this way, you can identify systems which have this very remarkable strong property. Okay, now having said this, we hereafter we'll focus again on a very simple system, which is now, the notation now is I go again back to t being the variable and so on. So we look at this system keeping in mind that we are particularly interested in the class of systems such that all the solutions are algebraic functions of t. Not analytic, but algebraic. I mean, of course, if they're analytic, they're algebraic, but this is a larger class. And I'll restrict, in fact, attention to the very, very simple one, which is this one, which is where the right-hand side is just quadratic. And there are two variables, so there are 6 arbitrary coefficients. And this system is the one that we study in this paper with François Levras and Robert Comte. And before going into the study, I have to, however, introduce an observation. François Levras has particularly emphasized this point. You see, this system here has 6 coefficients, C1 and so on, constant. On the other hand, it is clear that if you make a linear transformation from x1, x2 to other variables, which is linear with constant coefficients, the behavior of the system will not change in any significant way. A linear transformation contains 4 coefficients, because it's, maybe I've written a formula there. Yeah. Here, I forgot, because I should look what is that. Here I say that this system here, this system here, has been investigated 60 years ago by Garnier. And Garnier found out all the systems of this type that have solutions which are analytic. If you're now in modern words, it's a Painlevé property. They're all French, those who worked on this topic, but they worked on them some 60 years ago. And so that problem is solved. He was able to identify all the systems of this type which have solutions which are analytic. Now, our approach is, let us look, however, at equations with the solutions are algebraically solvable. So not analytic in the sense, not meromorphic in or holomorphic or meromorphic, but which may have branch points, but the branch points must be rational branch points. So solutions such that when you extend to the complex plane, the Riemann surface associated as a finite number of sheets. As a consequence, these systems are such that when you extend them with this trick of I omega, then they will be completely periodic. They will be isochronous. So that's the interest of finding them. And let me say immediately that we are not able to find all the systems that have this property, but we are able to find many systems that have this property. And as you will see at the very end, this is interesting even for a very, very, very classical problem. Okay, so this is what is written there, and this is the paper by Garnier. This is what I said, that we are interested because of the connection with this system. But before studying this system, as I said, there is the fact that you can make a linear transformation of this type. So here you have 6 arbitrary coefficients, but in reality, there should be only 2. And so the first step that we do in our paper is to introduce the notion of canonical forms of this system. And the canonical forms of these systems are, I have to go. Oh, I'm going backwards. That is why I don't get anything interesting. Here they are. So this is the idea, to introduce the canonical forms of these systems, which are the forms that you can obtain by linear transformation. They are not unique, but you can choose a particular set of them, and the set identified in our paper is this one. There is one which has 2 arbitrary coefficients of this very, you see, much simpler form. And then there are 3 more which have 1 coefficient, B, A here, you see. And then there are some very trivial ones which are here, just very, very trivial. So these are the general canonical forms of these systems. And so the task is, first we look at the general case. Can we identify a lot of cases in which this equation has all solutions which are algebraic? Now, how do you do that? How did we do that? Well, the point is that these systems are all, quote unquote, solvable by quadrature. Now, solvable by quadrature is a very bad way of naming things, because if you perform a quadrature, you can, in general, express time in terms of the variables. But that is not solving the problem. The problem is to express the variables in terms of time. And you might think that once you have time in terms of the variables, you just have to invert this relationship, and inverting this relationship is more complicated than solving the differential equation. So you have not made a great progress in this case, at least in the complex. So what we really want is to find the solution of this, or at least find a way to show that the solution of the problem is algebraic. And in many cases, we actually find them explicitly. And so I just give you the cases, the solution. I mean, the way to arrive at these results is that you do solve by quadratures, but then you look at the quadratures and you identify cases in which the quadrature are such, essentially, that you have a polynomial in terms of the variables, or the 2 variables, expressed in terms of time. And then, because it's a polynomial, to find these 2 variables, you just have to find the zeros of a polynomial, and that's an algebraic operation. And it implies that then, as a function of time, of complex time, it may have only algebraic branch points, and therefore it has this other property. So all the systems that have this property are not all the systems. We found that these systems have this property. We are not able to show that these are all. Maybe they are all, but we have not been able to show that. And so we focus mainly on the more general one with 2 variables. And then we found 3 cases. And the cases, you see, the assignment are very explicit. A has to be of this form and B of this form, where n is an arbitrary positive integer and r is an arbitrary non-vanishing rational number. So if this is true, then the solution, the general solution of this system will be algebraic. And in some cases we can actually show it, but we can show in general that it is algebraic. Of course, in some cases we can show it because if the polynomial turns out to be low degree, you can solve it, but otherwise you just show it. And so there are three cases. One is this. Another case is that where n is A is this, B is this, I is the imaginary unit. And again, n is an arbitrary positive integer, and R is an arbitrary non-integer rational number. And the third case is A is given by this simple formula, and n again an arbitrary positive integer, and m is an arbitrary integer of parity different from that of n. So there are an infinite number of such cases, of course. And finally, there is a special case in which A is minus 2 and B is equal to 0. And the solution in this case is explicit. It's a square root of a Weierstrass elliptic function. So being a square root, it is not analytic. I mean, it has a branch point, a square root branch point. Now, an interesting case is, let me go for a moment here, it's, you see, the more general case that we looked at was this one, the most general canonical form. Now let's look at the moment at the case when b equal to 0, and then in this case the class is just this class here, and this class is particularly interesting because by a change of variable, simple change of variable, you can reduce it to an equation which I think all of you have seen more than once in your life. This is Newton's equation. This a squared in front, you can even get rid of it by just rescaling z, clearly. And k is 1 or minus 2 over a. So, due to the previous results, the values of a are not very important, but the values of k, you can now show, we have shown that this equation is algebraically solvable for all these values of k, these two series of values. And I think in the next, yes, this is again reformulating these results in terms of you have eliminated a in front, so this is Newton's equation. You see I'm at the end, 32 over 34. This is Newton's equation. K is an exponent, and the assertion is that if this exponent has one of these values, it's an infinite series. You see, they're very simple to guess. Minus 3, 5 over 3, negative 7 over 5, 9 over 7, you can guess how it continues. And this other class is 0, minus 1/2, minus 2/3, minus 3/4. So you can guess how to, Now, we are, of course, talking about the properties of this very, very, very basic and elementary Newton's equation in the complex, not in the real. If it's in the real, you know very well what happens, but in the complex, it is not so simple. Of course, this is solvable by quadratures. Of course, it is integrable. There is the energy quantity. Note that here we have only one variable now. It's really just the most elementary Newtonian equations that you might think of. The one in which the force is just the power. And nevertheless, we believe that these results are new. I mean, that people did not know that all solutions of this equation with these peculiar values of k are algebraic when considered as function of complex variable. This also means that when you make this trick of the continuation, which you can do also for second degree equations, then all solutions will be isochronous, not only periodic, but periodic, all of them with the same period. That is the final result. Maybe I should say that this problem of investigating this very fundamental Newtonian equation has been investigated about 15 years ago by Piotr Griniewicz and Paolo Santini, but they looked at the case when k was an integer, positive integer. And they found, and their result was also very remarkable, that if k is a positive integer less than 12, the evolution, if you look at the evolution in the complex going around, is isochronous, I think, or periodic. But
it's only observation, it's not proof.
It's an observation, yes, because this was based largely on numerical tests. But more importantly, that if k is an integer larger than 12, then there is essentially chaos, whatever chaos means. In other words, the evolution is very, very complicated in a complex plane. Of course, if you look only at real values, it's very simple. But if in the complex, it's very, very complicated. And our result instead means that if you look at this equation with these peculiar values, for k minus 3 and k equals 0, of course, this was known that this was simple enough. But for the others is a new result. And as I say, this implies that then this system here, where lambda is, because of this change of variable, is 2 over k minus 1. You see, this is again an autonomous system like this. It's a generalization of, if you like, of the Newtonian equation. There is a time velocity-dependent term here. There is a kind of oscillator term here. Then there is the z to the k. And the relationship is this one, so that from this, by this change of variable with this assignment of lambda related to k, you get the new system, which is again isochronous. Then this system, if k is one of these, will be isochronous. And that's a nice result, as yet unpublished. So thanks for listening.
Are there any questions or remarks?
I have a remark.
Yes, please.
Now it is year 2020 rather than 2010.
La data.
Good point. Very good point, yes. Yes, yes. Well, you know, at my age, a decade is. I was 75 at that
time. Some psychological.
Yes, resistance.
I have a curiosity. Do you have any physical motivation for this problem?
Not yet. I should maybe emphasize that this type of systems, let's look at, let's go back maybe to this, but this basic type of systems, I don't think they are very interesting for physics, but they are very interesting in many, many other fields of applications, in biology, economics, evolution equation, you know, Lotka-Volterra type, and so on and so on. Many, many fields in which you have two quantities evolving, and then in some sense the simpler kind of modeling is of this type. So these are very applicable equations. But among the three of us, I was the one who emphasized this. The other two were only interested in the complex plane and analyticity properties. In physics, I don't think it is very interesting. I don't know. Now, maybe then it would be, you know, in some of these pseudo-physics models. Which, okay. But, yes. I think Piotr wanted to.
No, it seems to me that this algebraic integrability, some formula looks similar, some photograph transformation maybe. It's maybe some analogy.
Yes, maybe, yes.
Maybe some analogy.
Yes. Yeah, I should have, I don't have them in my transparencies. There are several examples in which explicit solution is given, but Maybe it's somewhat more general than the Hodograph transformation. And for one thing, you see, you can have an infinite number of Ks where you also.
Yes, please.
Do you apply the theory to the study, for example, of periodic trajectories? For example, we think about the harmonic oscillator is a polynomial, as a polynomial symbol. So maybe there could be an insight of that in this theory. But so I was asking if you applied.
Well, this is an approach that allows you to find many systems which are isochronous, which have all solutions which are periodic. That is also already done in a way. This is identified, a class of systems which have this property. The question then is that one can then look for applications in the literature, and that is a task for for the future, or for younger people probably in the future. But yes, this is an instrument to identify systems which have the property to be isochronous, and then isochronous is very strong, because it is not only to have all solutions periodic, but to have also solutions periodic with the same period. So it looks as if it is, it's an analogous harmonic oscillator, but it can be a more complicated system. I mean.
So we study only the case. So we study only the case in which the period is not depending on the energy in this case.
Yes.
Nothing about the case in which the period.
Yes, exactly. But as soon as you say the energy is because you have in mind classical mechanics. But as I say, this this class of equation is more applicable in other fields. I mean,
because I was connecting the fact that I was thinking the system in a physical way, and you're right.
I have a curiosity. In your solutions, your coefficients, your fractions are negative.
Yes.
Is there a reason why they're not positive? Or an accident?
No, I don't know. That's what they are. You see, the result is for these values of the K, the system has this property. As I said, we are not able to prove that these are the only cases in which this property is true. It might be true, but it is not yet proven. This is more difficult because you have to really make sure that they are. Garnier did and Panlevé also, of course, in another analogous case, identify all the systems which have the property, but in all those cases it was the property to be analytic in the sense of being meromorphic, or as a language, one-valued. Whereas these are multivalid, but finitely multivalid.
Are there any other questions? If not, let's thank